In the last lecture, we learned about two sets of vectors that you could associate to a linear transformation. Specifically, if T is a linear transformation from Rm to Rn, then there's the kernel of T, which consists of vectors inside of Rm, and the image of T, which consists of vectors inside of Rn. Now, the kernel and the image are very different from each other. In fact, they even live in spaces that are different dimensions. But it turns out that there are some similarities between them. So let's start with a simple fact, which is that the zero vector is a vector in the kernel of T. This is actually just another way of saying that T of 0 is equal to 0, which is true because of the linearity conditions. It's also true that 0 is in the image of T. This also follows from the same equation, that T of 0 is equal to 0, but we're looking at it in a slightly different way. When we say that 0 is in the kernel, it's because when you plug in 0 into T, you get 0. When we say 0 is in the image, it's because you can get 0 by plugging in 0 into T. So it's sort of looking at the same equation from the opposite perspectives. So another fact that's true is if x is in the kernel of T and y is in the kernel of T, then x plus y is in the kernel of T. And this comes from the fact that T of x plus y is equal to T of x plus T of y. If x is in the kernel of T, then T of x is equal to 0. And if y is in the kernel of T, then T of y is equal to 0. And so you get 0, which means that x plus y is in the kernel. So a similar thing is true for the image of T. If U is in the image of T and V is in the image of T, then U plus V is in the image of T. And the reason for this is that if U is in the image of T, then there must be some x such that T of x is equal to U. And similarly, if V is in the image of T, then there must be some y such that T of y is equal to V. And then we use the linearity property that T of x plus y is equal to T of x plus T of y. And in this scenario, T of x is equal to U and T of y is equal to V. So we get U plus V. And then the third fact is if x is in the kernel of T, then k times x is in the kernel of T for every scalar k. And there's a similar fact for the image, that if U is in the image of T, then k times U is in the image of T. I'll leave the proofs of these as an exercise for you. It's sort of similar to the proof for number 2, except you use scalar multiplication instead of addition. So these common properties that the kernel and the image both satisfy suggest that there should be some general concept that includes both of them. And that's exactly what leads us to the notion of a subspace. So a subspace of Rn is, by definition, a subset of Rn that satisfies the following set of properties. Property 1 is that the zero vector is in W. Property 2 is that if you take any two elements of W and add them together, then you get another element of W. And property 3 is that if you take any element of W and multiply it by a scalar, then you'll get another element of W. So these are exactly the three properties that we just saw that the image and the kernel of a linear transformation satisfy. So that gives us a big set of examples, that the image of any linear transformation and the kernel of any linear transformation, those are both subspaces. But there's actually another class of examples that we've sort of seen before, and that's the span of any set of vectors. Remember, the idea of span is that you have some set of vectors that you start with, and then you form linear combinations of those vectors by multiplying those vectors by scalars and then adding them together. So for example, if you have two vectors, v1 and v2, then the span of v1 and v2 is the set of all things of the form k1 times v1 plus k2 times v2. And it's worth going through the three conditions and just making sure that they work in this case. So for condition 1, we are allowed to choose 0 for k1 and k2. And then 0 times v1 plus 0 times v2 is the 0 vector. And so the 0 vector is a vector in the span. And then for condition 2, we can suppose that we have two vectors, x and y, that are in the span. So that would mean that x is equal to k1 v1 plus k2 v2 for some value of k1 and k2. And y is equal to L1 v1 plus L2 v2 for some value of L1 and L2. And then when you add x plus y, you can collect the v1 parts and the v2 parts together and get k1 plus L1 times v1 plus k2 plus L2 times v2, which shows that x plus y is again some scalar times v1 plus some scalar times v2, so it's in the span. And then I'll leave 3 for you to do. It's sort of a similar idea to 2. All right, so to get a better feel for what subspaces are and why we would care about them, it can be helpful to look at what subspaces look like for low-dimensional spaces, like R2 and R3. So let's start with R2. What do subspaces of R2 look like? Well, for R2, and actually for any dimension of space, there's always one sort of trivial example, which is a subspace that just contains the vector 0 and nothing else. It's actually worth kind of thinking through the 3 conditions of a subspace and understanding why it actually works. So obviously this contains the 0 vector, so it satisfies condition 1. For condition 2, if you take any 2 vectors in this subspace and add them together, then you get another vector in the subspace. And the reason for that is that the only vectors that you can take are 0, because that's all there is. So taking 2 vectors in the subspace means taking 0 and 0. And then when you add 0 plus 0, you get 0, which is another vector in the subspace. So it works. And actually, even though we call it the trivial subspace, it's not completely uninteresting. It actually plays an important role in the theory. You're going to be glad that it's there. So now let's suppose we have a subspace that's not just the 0 vector. Well, if it's not just the 0 vector, then it has to have some other vector that's non-zero. And because of the rules for a subspace, if there is some non-zero vector v in that subspace, then there have to be all of the scalar multiples of v as well. And then on the other hand, we know that the set of all scalar multiples of v is the span of v, so that is a subspace. And so these are exactly the subspaces that are sort of the smallest ones, besides the trivial one. And this subspace has a nice geometric interpretation. It's the line through the origin that's determined by v. All right, so lines through the origin are subspaces, and we also know that those are sort of the minimal ones besides the trivial subspace. So now we could ask what's sort of next up in the hierarchy. What if we had something that was bigger than a line? So this would be exactly the situation where your subspace has at least 2 vectors that are non-parallel to each other, so that one of them does not lie on the line formed by the other one. So in this case, all of the linear combinations of those 2 vectors must also be in the subspace. This is because scalar multiples of each vector have to be in the subspace, and then sums of those scalar multiples also have to be in the subspace. And so you can get any linear combination. But then on the other hand, the set of all linear combinations of u and v is a subspace. It's the span of u and v. And then this has a nice geometric interpretation, which is that you can move in any direction along u, and you can move in any direction along v, and together these 2 vectors fill out a grid that covers the entire plane, which actually means that the set of all linear combinations of u and v in this scenario is actually the entire plane. So this is kind of interesting. The vectors give us this weird coordinate system on the plane, but the subspace itself is just the plane. It's R2. And so actually we have found all possibilities for what the subspaces of R2 look like. There are exactly 3 different cases. There's just the 0 vector, there's lines through the origin, and then there's R2, which does count as a subspace of itself. And these are all of the possibilities for what subspaces of R2 look like. Now, we could actually do a similar analysis for R3. And I won't go through all the details, but actually if you look back at the arguments that were made for R2, most of them don't actually use specific properties about R2. So a lot of what happened there actually is still true for R3. In particular, you've got just the 0 vector all by itself, And again, the smallest subspaces that are not just the zero vector all by itself are lines through the origin. And actually, the key difference between R3 and R2 comes up in the next step, where when you have the span of two vectors, then those vectors will span a plane in three-dimensional space. And so you'll get a plane, which will be a plane through the origin. And then anything that's bigger than a plane will be all of R3. And so this is what all the subspaces of R3 look like. Just the zero vector by itself, a line through the origin, a plane through the origin, or all of R3. And one kind of interesting thing that you might notice when you look at these classifications is that you see the concept of dimension starting to come through. Like a line is something that you would think of as being a one-dimensional object, and then a plane is a two-dimensional object. And then you've got all of R3, which is three-dimensional. And so you can sort of imagine what the subspaces of R4 and R5 and R6 might be. They would be classified in a similar hierarchy where you go through the different dimensions of how large the subspace can be. So this is something that you can't really visualize once you get past R3, but one of the jobs of linear algebra is to make this concept more precise. So this sort of leads us to this question, what is dimension? And we're actually going to be answering that later on. Like we have intuition for R2 and R3, but what would we actually be talking about if we were talking about a five-dimensional subspace of R7? Pretty soon we'll be able to answer that question.